Hello, and welcome to lecture number 2 of 3 on Chapter 5 material, where we're learning all about forces. Now, last lecture I introduced you to Newton's three laws after a little bit of historical background and gave you a rough overview of what they were all about. Now, in this lecture, we are going to work lots and lots of problems. It's my experience that the best way to learn about forces is to actually work problems with them in there and use that to kind of help figure things out. So that said, we're going to start with a simple problem. How much mass does a person that weighs 200 pounds have in kilograms? Now, the reason why I'd like to work this problem is to introduce you to the concept of gravitational force. Now, there are a number of common forces that you see. For example, gravity, springs, tensions, and stuff like that we're going to be looking at today. And this is the first one, probably the most common force that you see. And that said, here's what we know. We have a person that has a weight of 200 pounds. So what's weight? Well, if you go back and you remember Newton's second law, I'm going to drop the sum notation and just write F external and let that be understood that that's the sum of the forces is equal to m times a. Well, all of the free fall problems that we've been working, we know that there's this thing that's called the acceleration due to gravity. Now, typically the way this is written when we're dealing with gravity is that the acceleration is written as g vector. Now, if you remember, g has a magnitude of 9.8 meters per second squared, or 32 feet per second squared, depending upon which system of units that you're working at. Now, when you add the vector thing, what you do is you attach the direction to g. So, for example, in all of the free fall problems that we've been working, the acceleration here might look something like minus g y hat. In the negative direction, this is this value, and this is the axis that it sits on. Now, thankfully for this particular problem, we don't necessarily need to use this equation. The reason why I wanted to work this problem is to introduce you to the concept of weight. Weight is the force due to gravity, is how gravity acts on you. Now, here on the Earth, there's a simple relationship between weight in pounds and mass. Kilograms is mass. Kilograms is how much matter is inside of you, how your body resists changes in its motion. So, as you go from place to place in the universe and you experience different accelerations due to gravity, the mass that's inside of you, you're resistant to those accelerations, if you will, does not change. So, as a consequence, your weight changes from place to place in the universe, but the amount of matter, your mass, does not. And that's the reason why mass is the useful thing to talk about in physics. It represents a quantity that generally doesn't change unless you have a system that has variable mass in it. Now, that said, the easy relationship here on the Earth between pounds weight and kilograms mass is this. There are 2.2 pounds of weight for every 1 kilogram. Now, the reason why I preface that by saying that it's here on the Earth is because on the Earth, you have your weight here, and if you were to go to the moon or go to Mars, your weight would be different. So, this relationship between mass being acted upon by the gravitational force to produce acceleration only works here. So, conveniently enough, though, this is a pretty easy problem, like I said. Your weight here, which I'm going to write as F sub g, this is weight, is equal to 200 pounds. Now, to get from weight to mass, if you're dealing with the imperial system, all you do is note the fact that for every 1 kilogram, you have 200 or 2.2 pounds. So if you do the math here, This is about 90.9 kilograms. Or if you stick with the significant digits that we have here rather, which is 1, this would be the same thing as 90 kilograms. So this is how much mass this person has. Okay, so this is mass. Again, mass is affected by gravity to produce acceleration. Now, thankfully, gravity always produces the same acceleration close to the Earth, which makes these sorts of problems relatively easy. Now, so let's work another. How many newtons does a 75 kilogram person weigh on the Earth? In pounds. What would their weight be on Mars, which has an acceleration due to gravity that is 1/3 of that, the Earth? So, we have a rough idea of what's going on. If you want to think of a person here, we'll say standing on the ground, and we're just looking at the weight would be down like this, being pulled down towards the ground due to the acceleration due to gravity, right? So here in magnitude, the weight of the person here would depend upon their mass and the acceleration due to gravity. So that said, let's write down our givens. We have a mass of 75 kilograms. Okay. The acceleration due to gravity here on the Earth, I'm going to put a sub e, is g. The acceleration due to gravity on Mars, I'm going to call that a sub m, is 1/3 of g. It's 1/3 of the Earth. We would like to find the weight on Earth, the weight on Mars, and also the weight here in pounds. Okay? So, we're going to use our gravitational equation right here. F sub g is equal to m times g. And take a look at here on the Earth, where our acceleration due to gravity is just g, cassette. So it would be 75 kilograms times 9.8 meters per second squared. So 75 times 9.8 is 735 newtons. Okay. Now, if we were to stick to the number of significant digits that we have here, that would be about 740 newtons, 2 sig figs. Okay, so this right here is on Earth. The weight on Mars would be m times 1/3 of g. So remember, this is the acceleration due to gravity on the Earth, and this right here would be the acceleration due to gravity on Mars. So it's going to be 1/3 of m times g. It's 9.8 meters per second squared. So, you do this and you get 245 newtons. So if you want to lose weight, all you really have to do is to go to another planet. Well, how well that's going to work. Anyway, so let's express this weight right here in pounds. So remember, on the Earth there are 2.2 pounds for every 1 kilogram. So 75 kilograms here times 2.2 pounds per kilogram is equal to 165 pounds. Or, if you round to sig figs, 170 pounds. So here's what we have. We have on the Earth in newtons, you weigh this. On Mars in newtons, you weigh this. But if you look at what you weigh here on the Earth in newtons, and look at the number of kilograms that you have, we can convert that to pounds. And here on the Earth, this right here would be what you weigh. Oh yeah, and we'll be consistent again with sig figs here. This is 245 newtons. This would be 250 newtons in sig figs. Okay, so both of these problems dealt with the common force of gravity. The next common force I want to look at is called the normal force. So here we have a block of mass 2.2 kilograms that's placed on a table, and it sits at rest. How much force does the table push back with? So this is an application of Newton's third law. So let's draw a table. There's the table. And here's the sort of show it's solid. Oops, here's our block sitting on top of the table like that. It has a mass of 2.2 kilograms. Now what I'm going to do is to draw a coordinate system. Up and down is in and out of the table, and side to side is the plane of the table. We'll label this y and label this x. Now let's write down what we're given. The block has a mass of 2.2 kilograms. However, we also know that gravity is working on this block, trying to pull it down. So this would be the acceleration due to gravity down like this. Right? So as gravity pushes this block into the table, according to Newton's third law, the table is going to push back on the block. So if you were to look at this from a force standpoint, the block experiences a force down due to gravity and its weight. But there's also a force up that the block experiences due to the table pushing back on it. Now it's this force right here, the force of the table on the block due to the fact that it's in contact with it and pushing on it, that we call the normal force. So the normal force is typically written as N with a vector, just like gravity is usually written as F sub g. Now, in this problem, I'm going to introduce you to a new tool. This is called a free body diagram or a force diagram. Now, all of the things that we're looking at here from a math standpoint, we're really thinking of as being little points in space with labels attached to them. So for example, this block here is drawn, has substance to it, but really it's just a point that says block on it, if you want to think of it like that. We're not at the point where we can add internal structure into things yet. So that said, I'm going to draw an XY coordinate system centered on my block. I'm not even going to bother drawing the block. I'm just going to put a little dot there. This is the block. Okay. Now, it has a mass of m. There are two forces acting on it. One force trying to pull it straight down to the ground, and one force pushing back on it due to the contact. Okay. So you have two forces here, the normal force and also the force due to gravity. Now, the reason why we draw free body diagrams like this is to help us find all of the external forces. So here, all of the forces that I have, when I add them up to find the external ones, okay, all of these forces here, just two of them, the force due to gravity and the normal force. Now, that said, take a look at the text of the problem. The block sits at rest. Okay? Now, Newton's first law tells you that if you have an object that is at rest and it continues to be at rest, there are no net external forces, which means when I add my forces here up, I'm going to get zero. No net force. Individually, the forces are non-zero, but added up, they cancel each other out. Okay, as you can see here. Now, that said, if you think of this as the y-axis and this is the x-axis, none of these forces have any part of them that lie along x. However, in the y direction, they do. I see, for example, that the normal force points along the positive y direction. I also see that the gravitational force points along the negative y direction. When you add these up, you get zero. Now, so if I want to find what the normal force is, which is ultimately what we're trying to find here, remember, how much force does the table push back on? All I do is solve for it. The normal force is equal to the force due to gravity in this case, in magnitude. Now, the equation for the force due to gravity is m times g. So, here, the normal force is 2.2 meters per, sorry about that, 2.2 kilograms. Doing so many kinematics problems, times 9.8 meters per second squared. Now, you may ask yourself at this point, oh, hold on, what about the negative sign here? Well, we've already taken into account direction right there. There is no negative anymore. Okay, it's already been dealt with. So here, the normal force is going to push back with this much force. 2.2 times 9.8. So 21.56 newtons, or if you keep to 2 sig figs, which is what we have here, 22 newtons of force. That's how much force it pushes back with. So this, like I said, introduces the concept of the normal force. And anytime you have something in contact with something else and it's pushing into it, a normal force is created. So for example, if you had a wall like this, and you push your hand into it like this, I'm going to draw a very poorly drawn hand there, you might exert a force this way, but the wall is exerting a force back on you, and this would be the normal force. Anytime you sit something on top of something else, gravity pushes into it, a normal force is created back. And the direction of the normal force is always at right angles to the point of contact. So here, this thing is in contact with the table, and the normal force when it comes out, sorry about that, the normal force when it comes out of the table like this makes a right angle to the surface. Okay. Now, so, like I said, another simple example. Let's do another one. A 5 kilogram mass hangs at rest from a massless string attached to the ceiling. What is the tension in the string? Now, this introduces the common force of tension. Tension, strings, ropes, pulleys, these sorts of things are incredibly important, and they form the foundation for most basic simple machines. Now, One of the properties of tension is that in a rope or a cable or a string, the tension is the same at all points. And I'll show you why that's the case here in a moment. That said, let's draw our picture here just to sort of get a feel for what we're looking at. So here's the ceiling. Here's our rope or string. And I don't know, maybe here's our mass. Now, so the mass is 5 kilograms. All right. Now let's talk about the properties of a rope or a string or something like that. Now, as this pulls down due to its weight, the string is attached to it and is pulling back. This is tension. The rope pulls the string taut, and as a consequence, the fibers of the string pull back, if you want to think of it like that. Now, were I to grab the rope or the string here and lift with my hand, ignoring the mass of the string, I would be lifting 5 kilograms. If I were to lift here, ignoring the mass of the string, I would be lifting 5 kilograms, which means that the force that I would be feeling here due to me pulling on the rope and pulling it upwards would be to the rope pulling down like that, conveying the force of this weight. It's the same here too, and even the same here at the very top. What that means is that the tension at any point inside this rope is the same. Now, that said, two forces are present. We have, again, the force due to gravity this way, and then we have the rope being pulled taut up like that. So two forces, like I said, the tension force, which we're going to call T vector, and the gravitational force, F sub g. Now, let's write out our givens. The mass is 5 kilograms. And what are we trying to find? We're trying to find the tension in the string, T vector. Okay? Now, so we have a picture, we have what we're given, what we're trying to find. The very next thing you do when you're dealing with forces is to draw your free body diagram or your force diagram. Once again, I'm going to draw an XY one with the point of contact or the mass right here at the center. Here's Y, here's X. Our mass feels a tension due to the string and a weight due to the force of gravity. Tension, weight. Now, just like before, we add up all of the forces to get the net external force. In this case, when we add up our forces to get the external force, there are only two: tension and weight. Now, this thing hangs from rest, and as before, what that means is that it's going to stay at rest and that our forces, when they add up, give you 0. If I look here, the tension goes up the positive y-axis. It goes down, or the gravity rather, goes down the negative y-axis. There are no components of either in the x direction. So if you were to add them together in the y direction, you have tension up, and then you have the weight going down. and they give you 0 when added together, which means that our tension, once again, is in magnitude just due to the weight. M times G, or 5 kilograms times 9.8 meters per second squared. Now, when you do this, you get 49 newtons. Keeping to the number of significant digits that we have, that's 50. Now, the magnitude of the tension is 50 newtons. We're asked for the tension. That's a vector. At least in this case, as drawn, it would be T vector is equal to 50 newtons in the y-hat direction. Now, let's work another. A mass of 15 kilograms hangs at rest from the pulley system below. What is the tension of the ropes? Now, once again, we're dealing with the common force of tension. The reason why I want to work this problem is to show you some of the unique and very useful properties of tension. Now, this rope wraps around like this and holds up. Okay, so this is a bad picture. What time is this? 27 minutes in? All right, so let's erase this picture, and then we'll come and we'll work this again. All right. Okay, so let's work another. A mass of 15 kilograms hangs at rest from the pulley system below. What is the tension in the ropes? So this is another example of a tension problem. The reason why I wanted to do this particular one is to demonstrate how useful tension is. Now, in this case, we have a rope that's wound around a pulley like this, and then we have a cable holding the mass in place on the pulley. Now, we're going to assume that our pulley and that our ropes are all massless. We need to make that assumption, at least initially. Later on, when we develop a more useful understanding of what's going on, we can amend that and actually add in some internal structure. But once again, we're dealing without any masses or anything like that for right now. Now, that said, The important thing is that this rope winds around it, okay? So that means that even though you have a force here due to gravity, due to this mass here, this rope right here is splitting that force up both sides because it's wrapped around. Now remember, the tension is the same at all points inside a rope, which means that if I were to ask what the tension is here, or what the tension is here, or even what the tension is here as it wraps around the pulley, I should get the same number, in magnitude. Obviously, the direction is going to be different, but, that's the idea here. So that said, what are we given? We're given that the mass that we're dealing with is 15 kilograms. What are we trying to find? The tension in the ropes. Really, it's just the tension in this rope right here. Okay? Now, so we're going to disregard the tension in this, but just to show you how it would work, gravity pulls this down and causes this to become taut. This tension conveys up to here and allows the force to be transferred and to pull the pulley down. It's this downwards pull due to the rope here that's actually being conveyed up both sides here. Okay? Now, that said, let's draw a force diagram on the pulley. So, once again, you have the y direction, you have the x direction. Now, you have the weight of that mass pulling down. But you also have tension being split up both sides. There's two vectors going up here. Now I'm drawing them a little off axis. They're not on the x-axis. It's just because there's two of them here. I need to be able to separate them on that axis there. Now, this is the same rope. Okay, this is the same rope. And what that means is that this tension right here and this tension right here would be the same, because tensions inside ropes and in cables and in strings are the same at all points. This is gravity pulling down. Now, this thing hangs at rest, which means that when we find all of the external forces here, when we add up all of the forces, of which we have three now, we have a tension going up, we have a tension going up, and we have a weight going down, that we expect to get zero. Now, here, both tensions point up the y-axis, so they're positive. T plus T. Again, this is in y. There's nothing interesting going on in x with this problem. We have gravity pulling down, and those should add up to zero. So check this out. 2 times T minus Fg is equal to 0. Or if you solve for the tension is half of the weight. Okay? So here, 1/2 of 15 kilograms times 9.8 meters per second squared. So if you do the math there, half times 15 times 9.8 is 73.5 newtons. Now, obviously to 2 sig figs, this is going to be 74 newtons. But look, it's half of that, half of the weight, because it's being split up both sides. So what that means is that by using a pulley, you can actually reduce the load, reduce the amount of force, the amount of stress that a cable or a string or something like that experiences by splitting the force. Now, later on, we're going to work more complicated problems where you can actually use pulley systems to reduce the amount of force that you would need in order to lift something like this. Okay. So it's all by splitting these forces around that tension is able to do the job. Now, it's an incredibly, incredibly powerful tool. Just as an example, imagine, having a pulley like this. So maybe you pull down here, but you're pulling something over here. So what I'm able to do also with tensions is to take and redirect the direction of a force by bending the cable or the string or the rope. So that's the reason why these things are so powerful. Now, that said, let's do another problem. Let's box that too. There. So if you wanted to be technically correct about this, you'd say that the tension in the ropes here would be, oops, wow, that's interesting. I drew that with boxes. There, it's better. So the tension here would be 74 newtons y hat. Okay? Now, so let's work another. Okay, so thus far we've dealt with the common forces, gravity, the normal force, and tension. Now we're going to deal with another common force, and that's the spring force. Now, spring forces are called restoring forces. Now, the way a spring works is like this. So imagine having a spring, say sitting up against the edge of the wall. Here's my spring right here. And it's hanging stationary. Okay, it's just sitting there stationary. There's no force being exerted on it. So it has a relaxed length. And the end of the spring where you would connect something is at a location that we typically would call the equilibrium position. Equilibrium meaning in balance. It's neither pulling or pushing. Now, springs are funny creatures in that if you push on a spring like this and you compress it, the spring pushes back on you. Now, it's pushing back on you to try to get you back to the equilibrium position and stay at as close to its relaxed length as it can get. It's restoring you back to equilibrium. If you were to pull on a spring like this, the spring would pull back on you like that. Once again, trying to restore you to some sort of equilibrium position, some sort of position where the spring and the pull or the push are balancing each other out. Okay, so spring forces are examples of restoring forces. Now, there is a law called Hooke's law that describes how springs behave. I'm going to call spring forces F sub S equal to minus K, which is a constant, and I'm going to tell you what that is here in a second, times R. Now, K is called the spring constant. It has units of newtons per meter. So, for example, if you had a spring constant that was 100 newtons per meter, what this means is that if I were to compress your spring or stretch your spring by 1 meter, you would have 100 newtons of force acting on you. That's because the relationship between the force and how far you compress this thing is linear. So if I were, for example, to compress it by 2 meters, I'm going to have twice the amount of force here. 200 newtons, either trying to push me back to equilibrium or pull me back to equilibrium, depending upon whether I'm stretching or compressing. Now, Hooke's law is the law that we're really interested in because it describes how springs generate forces depending upon their constant and how far they've been compressed. In this example, though, we're thinking of a spring that's hanging off a ceiling. So here's a ceiling. Here's our spring. Maybe this right here is this relaxed length, the equilibrium position. And when you take and you hang a mass off of it, it stretches to here instead. So this point right here would be at the end. And you see how it's been stretched from here to here? This right here conventionally is what R would be. Because at its relaxed length, where the spring is neither pushing on you or pulling on you, it's exerting no force. If it's exerting no force, that means that R, your position, we say is at zero or at equilibrium. Okay? So, what we're looking for is how far this spring is going to stretch due to the fact that we have this mass hanging off of it. So, let me draw another better picture here. I'll put it right here. Here's our spring. Here's the mass hanging off the end. Maybe this right here was this relaxed length. We'll say y is equal to 0 at this point. And right here is going to be its stretched length. This is what we're trying to find. Now, we have a force due to gravity pulling down on the mass. We also have the spring, trying to restore the mass to its equilibrium position, which is pulling back like that. So we have a spring here, a spring force, and we have the force due to gravity. Now, if this thing if we let it relax and come to rest, what that means is that when we look at the external forces here, when we add up all the forces that are acting on the mass here, we should get 0. So to show that, let's draw a force diagram. We have the spring acting upwards, gravity pulling it downwards. Okay. Now, so we have a free body diagram. We have a picture here showing us what's going on. Let's go ahead and write down our givens and what we're trying to find. I'm going to erase a little bit of this to clear up some room. Let me just get rid of this right here. So we're given a spring constant of 30 newtons per meter. We're also given that the mass that's hanging off the end of it is 2.5 kilograms. Now, why is this thing stretching? Well, that's because of gravity. Okay. What are we trying to find? We're trying to find how far it's going to stretch, which we're going to call y simply because of the fact that no component of this force lies along the x, it's strictly along the y direction. And since r is a spatial thing, it's a position vector, we're going to just use y here as opposed to r. So I'm going to add my forces up to get the external force. I have two forces present. I have the spring force, which is pulling upwards, and I have gravity, which is pulling downwards. But they have balanced each other out to give you 0. So what that means is that if I add these things together, taking into account the direction along the y direction, or along the y-axis rather, we have a positive spring force, but a negative weight. Okay? And those add up to give you 0. So here's what we have. The spring force minus the weight is equal to 0. Now we know weight looks like mg. The spring force in this case, because we've already taken into account the fact that it's trying to restore it upwards, has no negative sign in the front and looks like k times y, y being the distance that has been stretched. Okay? Now, if we plug these things in here, I have k times y minus mg is equal to 0. We know g, that's just 9.8 meters per second squared. We know the mass, that's easy. We know the spring constant, and we're trying to find y. So if you solve for y, it's mg over k. M is 2.5 kilograms. G is 9.8 meters per second squared. And K is 30 newtons per meter. Now, if I plug this into my calculator, I get 0.817 meters. Now, I see one sig fig here, I see two sig figs here, which means that this is going to round out to 0.8 meters. This is how far the spring is going to stretch. So, how far does it stretch? 0.8 meters. There's your answer. Now, we'll come back to doing more spring problems later on, but this is yet another example of a common force. So far, from a common force standpoint, we have gravity, we have the normal force, we have tension, and we also now have springs. Okay, these are primarily going to be the normal forces, other than just exerting a force by pushing or something like that we deal with for quite some time. Okay, so let's work another one. So in all of the problems that we worked previously, we were dealing with an object that was at rest. Not only that, the net forces added out to 0. So those are examples of statics problems, and I'll give you a more formal definition of statics in a little bit. That said, this is an example of a dynamics problem, and it's probably one of the better introductory examples, we'll say, that introduces the gameplay when forces are at work. Okay, so we have a rocket that's in space. It has an engine that can produce 2,500 newtons worth of thrust. If the rocket has a mass of 50,000 kilograms, what acceleration does it experience? If the rocket starts from rest, where is it, and how fast is it traveling after 2 hours worth of acceleration? So let's draw our picture. I'm going to have our rocket move along the x direction, like that. So here's our little rocket ship. Maybe it looks something like that. Who knows? Okay, it has a mass. The mass is 50,000 kilograms. Okay, now it starts from rest. Okay, we're going to let our initial position be 0. It accelerates to the right, and at some point over here, 2 hours into the future, we would like to know its position and its velocity. Now, what's causing the acceleration? Well, before, that wasn't a question we can answer. But in this case, it's the thrust from the rocket, which we're actually going to talk more about when we get to momentum. So, the force, if you want to think of the push of the thrust this way, is what's doing the job. And I'm going to call that F sub t. Okay? Now, in this case, the magnitude is 2,500 newtons, and the direction is in the positive x. Okay? So, here's our problem. We have it laid out. Let's write down our givens and what we're trying to find. We're given the magnitude of the thrust is 2,500 newtons. We know it's in the x direction as drawn. We're given the mass of the rocket as 50,000 kilograms. We're given an initial velocity in the x direction as 0. Obviously, y is 0 as well, but I'm going to be consistent with the notation that we adopted back in chapter 4 by labeling things along particular directions. We're looking 2 hours into the future. Now, we're going to need to convert this, but we know that 1 hour is the same thing as 3,600 seconds. So if you convert 2 hours to seconds, that ends up being 7,200 seconds. We also, because of how we've drawn things, decided to start with an initial position in the x direction of 0. Now, what are we trying to find? We would like to find out the acceleration in the x direction. We would like to find its velocity and its position after the given time. The next thing you do is to draw a force diagram. In this case, we only have one force, and it's explicitly along the x direction. Here is our rocket right here, and the force goes this way. Now, in the previous problems, there was always a second force to balance things out, or possibly even a third, like for example with the previous tension problem. In this case, there are no forces to balance out stuff, which means that because we have a change in motion, because this rocket starts from rest, it ends up with a velocity that's not 0 later on, we have this force at work. That means when we add up our forces to get the external force, it is not 0. In this case, our forces added up are what causes the rocket to experience an acceleration. Okay? Now, so here we only have one force. When you add it up, it adds in as the tension, or not the tension rather, but the thrust. Okay? So, m times a vector is equal to f vector. But look, in the y direction, there's nothing interesting going on. So that means really we're only looking at the x direction. We know from our picture that our acceleration is going to be this way. That's the direction that things are quote unquote being pushed, which means that everything is positive. It adds in as a positive. Okay? So the acceleration that you have here is just the thrust divided by the mass. Now, this is typically the way things are done with forces. You draw your picture, you look at what you've been given, and the free body diagram here dictates the forces that are present that can cause accelerations. Once you have your acceleration, then you can find positions and velocities. So this right here really is the gateway to getting your equations of motion at the end of the day. Now, that said, since we're dealing with a constant force, that means that we do also have a constant acceleration. And we already have a series of equations developed that can help us deal with that. Those are the kinematic equations, of which we have three. In the x direction, they look like Vx is equal to V naught x plus Ax times t. X is equal to x naught plus 1 half Ax times t squared plus V naught x times t, and Vx squared minus V naught x squared is 2 times Ax times x minus x naught. So here are three equations of motion. Like I said, there's nothing interesting going on in y, so we don't have to worry about it. It's just the x motion that we're looking at. So let's put in our givens here that we can use to simplify. Our positions, for example, initially are all 0, and our initial velocity is 0 as well. That goes away. That goes away as well. That's 0 as well. So out of these three equations, they simplify down pretty good. Vx is equal to Ax times t. X is equal to 1 half Ax times t squared. And Vx squared is equal to 2 times A times x. Now, so the first thing we're asked for is to find the acceleration. We can just go ahead and plug the numbers in for that. It's pretty easy. Ax is equal to the thrust over the mass. The thrust was 2,500 newtons. And the mass here is 50,000 kilograms. So when you take 2,500 and you divide it by 50,000, you get this. Excuse me. 0.05 meters per second squared. Now, this may not seem like much at all, but you're going to be pretty surprised, I think, at the result. So here's our first thing. Conveniently enough, we have two sig figs here. We have one here. This is one. And that's how it turned out. So, lucky. So, we have gotten our acceleration. What's our acceleration? Zero point zero five meters per second squared. Okay, so let me make a little room. I'm going to erase our cancel out kinematic equations here just to make some room here on this so we can have the picture and everything in our view. Next up, we have velocity we can find, and we have position that we can find. We can based off of what I have here, since we have time already, it really doesn't matter which one we do first. I propose we find velocity just for the heck of it. Velocity at this acceleration at 7,200 seconds in the future is going to be give me a second here, 0.05 times 7,200. 360 meters per second. Okay. Now, obviously, when we, at the end of the day, write this down as an answer, we're going to have to round to one sig fig, and that's going to round to about 400 meters per second. Okay. Now, how far did it go? We could use this equation. We could use this equation. It really doesn't matter. I'm going to use this one right here. X is 1 half Ax times t squared, 1 half 0.05 meters per second squared times 7,200 seconds squared. So 0.5 times 0.05 times 7,200 squared. And that ends up being something like 1.296 times 10 to the 6 meters. Okay, now keeping to within 1 sig fig, obviously this is going to be 1 times 10 to the 6 meters in terms of distance, but that's pretty far. See, slow accelerations like this over large amounts of time can take you very, very, very far. So here's what we have: 1 times 10 to the 6 rather meters, and here's our answers right here. What's our acceleration? It's this. What's our velocity? It's this. And what is our position? It's this right here. So this would be an example of a type of problem called the dynamics problem. Okay, so statics problems are ones where the velocity is 0 and the forces add up to 0. Dynamics problems are ones in which that's not the case. Okay, so let's do another example. A box is pushed by a person with a force of 225 newtons and with an angle of 15 degrees below the horizontal. What is the normal force in the box? What is the acceleration of the box? If the box starts at rest, where is it after 5 seconds of pushing? Assume that should be that. Assume that the box has a mass of 25.0 kilograms. So, once again, we start with a picture. So this is your first example, really, of a series of forces acting on something that's not just along the x direction or just along the y direction. This is an actual full two-dimensional problem. So here's our box. Excuse me. It has a mass. The mass of the box is 25.0 kilograms. Now, it's being pushed. We're going to have it being pushed to the right. Okay. So at some point, and I'll draw a little sort of fake dashed box here. At some point over here, we're pushing on the box, and boy, that was a weird effect. And it's over there now. Now at this point right here, position X, which we don't know, we're trying to find that. Let's see. We have a velocity initially in the x direction that's 0. We're going to let this thing start off at the origin. Now our push here is 225 newtons, but it sits at an angle of 15 degrees below the horizontal. So the way to think about that would be you have a person, we'll say, right here. And they're pushing the box like this. But the way that they're in contact with the box and pushing is down like that. So if you think of this right here, let me see here. If you think of this as being parallel to the x-axis right there, then we have an angle right here that's the 15 degrees. Okay, so our force here is 225 newtons. I'm going to call it the force of the push, and it makes an angle of 15 degrees below x. All right, now that's not the only force that we have present, because obviously this thing is sitting here on the ground, it's being pushed. Let me just sort of draw a ground here to show that it's on the ground being pushed. And there's gravity trying to pull it down into the ground. Okay, so there is in fact a force due to gravity. Let me draw that a little bit more straight, like that. So there is a force due to gravity right here as well. Now look, you're pushing partially into the ground. Gravity is also pushing this thing into the ground, which means that you have a normal force present too. That normal force, remember, always acts at right angles to the ground. So here, our normal force is going to push up like this. So right angles to the point of contact is what I should have said. Sorry about that, not necessarily the ground. So here's your normal force right there going up. And this is one of the things that we have to find. So there's a lot of information here, but at the end of the day, we're finding our forces and we're using our forces to generate the motion. And that's how it works. Remember, forces cause changes in motion. That's Newton's first law. The relationship between the force and that change is through Newton's second law, F is equal to ma. All right. So at this point right here, how long in the future do we say it was? 5 seconds. Let's just finish labeling our box. We've got our mass here. It's a little obscured here, but it's still there. We have our angle. Yep, that looks good. Okay, so let's write down what we've been given and what we're trying to find. Okay, so we're given the box has a mass of 25.0 kilograms. We're given that we're looking 5 seconds into the future after our push. We're also given, based off of our picture, v naught x is equal to 0, and also x naught is equal to 0. Now, again, this thing is only moving along x, but that's because the ground is preventing the box from being pushed into it. The forces that we have at work are also along y as well. Now, speaking of which, the force of our push is 225 newtons, but it makes an angle of 15 degrees. I'm going to put minus sign here to signify below the x-axis. In practicality, we're not going to be using the negative. Remember, we always like to, or at least I personally always like to deal with angles that sit between 0 and 90 degrees. So, but we'll get to that here in a second. Now, what are we trying to find? We're trying to find the acceleration of the box. We're trying to find where it is after 5 seconds of pushing. And we're also trying to find the normal force. Okay, so that said, let's draw us a free body diagram. And now you can really see why the free body diagrams are so essential. Because we got a lot of forces here, and not all of them are easy to deal with. So we have the y-axis, we have the x-axis. X is along the ground, y is obviously up at 90 degrees from the surface of the ground. Here's our mass right here at the center, and we have gravity pulling this thing into the ground. Whoops, let me fix that again. There. We have the normal force of the ground pushing back on it, like that, and then we have this push that sits below, like that. Normal force, gravity, and the push. Now, it's this image right here, this picture right here, our diagram for the free body, that's going to allow us to do useful things. So, here, when I add up my forces to get my external forces, or total external force, I have 3. I have a normal force, I have the force due to my push, and also have the force due to gravity. These are not going to cancel each other out. Okay? Now we do know that because the ground presents an unyielding place, that the normal force and whatever down stuff are going to cancel each other out. And that's due to Newton's second law. But if you look at our picture here, there is a part of our forces that lies along the positive x direction that has no equivalent in the negative to cancel things out. And that's part of our push. So what happens here is the following. Part of the push is into the ground, and that's going to cause the normal force to actually get bigger than it would be if it were just due to gravity. but part of the push is also along the ground. And that's what's going to be giving our box the acceleration at the end of the day that causes the change in motion that we see. Now, so we have stuff going on in the y direction, and we have stuff going on in the x direction. In the y direction, I see a normal force that points upwards, so it adds in as a positive. I also see gravity that sits exclusively along the negative y direction, so that adds in as a negative. Now, our push here, though, has got part down, a y component that's down. So there is a part of our push that is down. Now, in this case, your forces along y add out to 0. And that's because, again, the ground is an unyielding object. You can't go into the ground. So the force that the ground produces to react against gravity and this downwards y part of the push is going to exactly balance them out. On the other hand, there is one force and one force only that has an x component, and that's the push, like that. Now, this most definitely is not 0. It's equal to the mass times the acceleration of the box. Okay? So here's what we've done. We have taken our picture and produced a free body diagram. And it's from the free body diagram that we're able to do useful things like get the sum of the forces here to find what the normal force is eventually, and also find out what the acceleration is. Now, that is, however, going to require that we break up this force right here, this push, into pieces. Now, I want to be very clear. I've already put the direction in. So there's no reason to put a negative 15 degrees here. Our angle here, as drawn, may be 15 below, but we're dealing with angles that sit between 0 and 90 and letting common sense dictate the direction. So here, this would be the part of the push that's in the y direction. This would be the part of the push that's in the x direction. This right here is 15 degrees. And this right here is the push in entirety. And in fact, just to make myself clear, I'm going to scratch the 15 here, the negative part off the 15, just to be very clear that our angle is in fact 15 degrees, but it's just below. Okay. So we're going to need to find FPX. We're going to need to find FPY. If we write out our trig functions, we'll note that FPX is the adjacent part, FPY is the opposite part. So FPY is going to be FP times sine of theta. FPX is going to be FP times cosine of theta. All right, so these two equations right here say the following. The normal force minus the weight is m times g, minus this downwards push, which is Fp times sine of theta, is equal to 0. And it's this equation right here that's going to give us the normal force, because we know how much of push we have. We know the mass of our box, and we know the angle below the horizontal that we're pushing at. So we can solve this one, and in fact, we will solve this one immediately here in a second, to find out what the normal force is. Now, the second equation says this. The force of the push times cosine of theta is equal to m times a sub x. And it's this one right here that's going to give us an equation of motion. Okay, this is going to give us our acceleration. Since our acceleration is constant, we'll be able to use our kinematic equations to do stuff. Okay, now let me page down here just a touch. Since we have a pretty good idea of what we're looking for, let's just go ahead and get the normal force. So the normal force, using this equation right here, is equal to mg plus f sub p sine of theta. Now, that's 25.0 kilograms, 9.8 meters per second squared, plus 225 newtons times sine of 15 degrees. Why not negative? we've already taken into direction, or taken a direction into account, rather. It's already been taken into account right there. So when I solve for this, let me go ahead and put this in my calculator. Sine 15. I get 303 newtons. So if I look at my sig figs, I have 3 here, I have 2 here, I have 2 here, I have 3 here. So this would be 300 newtons, or actually, probably better written as, to show the sig figs, 3.0 times 10 to the second newtons. So can actually get the sig figs there. And the normal force itself is going to be up, like that. So here's the answer to the first part. We were asked, what's the normal force? Okay. Now, the next part deals with the dynamics of the situation. We wanted to find the acceleration, but we also want to find out where it's at after 5 seconds. This equation right here is going to give us our acceleration. If I solve for a sub x, it's f sub p cosine of theta over m, or 225 newtons cosine of 15 degrees divided by 25.0 kilograms. Now, if I solve this, this is 225 times cosine of 15 divided by 25. Whoops, math error. Fix this. I wonder what your math error is all about. Strange. There we go. Okay. It's calculator being stupid. So the acceleration itself ends up being about 8.16 meters per second squared. Okay. Obviously, to sig figs, it's 2, so that would be 8.2. Meters per second squared. There you go. Now, so the last thing we wanted to find out was the displacement. We'll write down our 3 equations of kinematics here. Vx is equal to v naught x plus ax times t. X is equal to x naught plus 1/2 ax times t squared plus v naught x times t. And then vx squared minus v naught x squared is equal to 2 times a sub x times x minus x naught. Now, here, I would say, since if you plug in our initial stuff, we know our initial velocity and positions are 0. It's just like before. That's 0, that's 0, that's 0, that's 0, and that's 0. I would personally probably use this one right here, this equation, to find our position, because we know everything that's in it. Now, here you would want to use the full expression of your acceleration from your calculator. I'm going to put this just because it's written down. And the time we're looking at is 5 seconds. So, excuse me. So this would be times that times that times that. I get about 102 meters, which to 2 sig figs ends up being 1.0 times 10 to the second meters, so we can actually preserve the number of significant digits. So there you go. All right. Now, let's work another. A traffic light hangs at rest from two cables. If the light has a mass of 25 kilograms, one cable hangs with an angle of 20 degrees with respect to the ceiling, and the other hangs with an angle of 45 degrees. Find the tension in each cable. So, here's the ceiling. Could be a light pole. Here's, whoops, wow, that's actually a surprisingly good thing. Here is one cable. Here is the other cable. And maybe here's a little connector right there. And there's our traffic light. Maybe it looks something like that. So I'm going to call this one right here, this angle right here, theta 1. And this angle right here, theta 2. And as a consequence of the mass that this thing has, and gravity pulling down on it, what that does is to tension this cable and to tension this cable as well. So the tension that's in this cable I'm going to call T1, and the one that's in this cable I'm going to call T2. All right. Now, so you have tensions that are heading up the cables like that, right? But then you also have the force due to gravity pulling down on this thing. F sub G. Okay. Now, this thing hangs at rest, so unlike the last dynamics problems that we've been doing, this is an example of a statics problem. It is at rest, and the forces are going to add each other out. Okay, they're going to add out. So, what are we given? Let me just go ahead and explicitly put in the angles here. That theta 1 is 20 degrees. Theta 2 is 45 degrees. The mass of our object here is 25.0 kilograms. Okay. Now, what are we trying to find? T1 and T2, we already have the directions because of the angles and stuff, but you'll see that. There. So we have a picture, we have givens, we have what we're trying to find. The next thing we do is to draw a force diagram. I'm not happy with that y-axis. Okay, so what I'd like to point out before I start drawing stuff here is that if you look at our picture, this right here is a line that would be the x-axis, which would also be parallel to the ceiling. Okay? Now, why is this relevant? Well, look, if you go back and you sort of remember your geometry from way back in the day, if you have two lines that are parallel to each other and you have a third line that intersects them, you know things about the angles. For example, if this is theta 1 right here, this right here is theta 1 as well. If this is theta 2 here, this right here is theta 2. So what that means is that when we draw our picture over here and we label stuff like that, we already know what our angles are. So we don't have to do anything complicated to find them. This is theta 1. This is theta 2. Y-axis, x-axis, and then we have gravity going down like this. Maybe I should turn snap to grid back on. Nah. So this is our weight. This is tension 1, and this is tension 2. And these are the things we're trying to find. Okay. Now, so just like before, we have our net forces that are acting on this thing, or all of our individual forces, rather, that are acting on this thing. Let's sum them up to find out what the total external force is, which we already know is going to be equal to 0 because this thing hangs at rest and it's not experiencing any motion that's changing. So we have 3. We have tension 1, we have tension 2, and we have the force due to gravity. Now remember, they add in. Okay, they add up like this. But at the end of the day, when we look at what's going on in the x direction and we look at what's going on in the y direction, that's when you have to take and put in negatives and things like that. And on that note, let's look at x. So the force due to gravity lies entirely along the y direction. But the tensions that we have here both have x parts. Tension 1, for example, has got a positive x part, and tension 2 has got a negative x part. Now, those are going to cancel each other out. So here, when you add them in, you have tension 1 that has an x part, and then you have tension 2, which adds in as a negative because it points down the negative x-axis. And those are going to cancel each other out. Now, in the y direction, you have an x and y part, or not x and y. You have a y part of T1 and a y part of T2 that point up the positive direction, and then you have gravity pointing down. Now, those are going to cancel each other out. So you have T2y plus T1y. Those are positive. And then you have gravity coming in as a negative like that, adding out to 0. Okay? So these are our equations right here. They're going to, give us what we're looking for. And really at this point, we're done with the physics. We're basically just doing math now. Now, what do I mean by math? Well, we have 2 vectors here, and we need to break them up into components. Now, we may not know what T1 and T2 are yet, but we do know what the angles are, and we're going to use that to our advantage in a little bit. All right? So, this right here we'll say is T1. This would be T1y, and this would be T1x. And this right here would be theta 1. Now again, noting the fact that T1y is opposite and T1x is adjacent, we can write T1y as T1 times sine of theta 1. Just like we can write T1x as T1 times cosine of theta 1. Now we know theta 1, thankfully. Okay, we don't know what T1 is, but we're going to find it. Now, let's look at the other one. T2 looks like this. Oops. It has an x part. It has an x part, and it has a y part. Now, so this is T2. This is theta 2. This is T2y and T2x. Now, again, direction has already been taken into account. Everything that we're dealing with here is positive. But noting again the fact that T2y is opposite and T2x is adjacent, T2y can be written as T2 sine of theta 2. And T2x is equal to T2 times cosine of theta 2. All right? So what that means is we can take our two equations here and plug in into t1x and t2x and the t2y and t1y. These right here. Okay, that's what we want to do. It's going to get a little messy, but at the end of the day, it's just algebra. I laughingly say that because algebra, it turns out, is actually the hardest math you can do. So we'll start with this equation right here. This equation I'm going to put right here. T1x is T1 times cosine of theta 1 minus T2x. T2x is T2 times cosine of theta 2. Those are going to add to 0. This equation right here says T1 sine of theta 1 plus T2 sine of theta 2 minus mg is equal to 0. Because remember, weight is just mg. Now, is this the prettiest thing in the world? No. I never said it was going to be pretty. But look what we have. We have two equations in which we know the angles, we know the mass, we know g, and the only things that we don't know are T1 and T2. Two equations, two unknowns. This is a completely solvable system of equations since the equations are different from each other. Now, typically what you do is you take one equation, you solve it for, say, T1, and then every time you see T1 in the second equation, you plug it in. And what you'll get is an equation that is entirely in terms of T2, and you can solve for it and then go back to the old equation and find out what T1 is. That's exactly what I'm going to do. So let's take this equation right here and solve it for T1. If you do that, you get that T1 is equal to T2 times cosine of theta 2 over cosine of theta 1. All right. Now we're going to box this because we're going to need it later on, and I don't want to forget where it's at. Now, every time I see T1 here, I'm going to plug in this. So if I do that to this equation right here, I have T2 times cosine of theta 2 over cosine of theta 1. That's this right here. That's T1. Then times sine of theta 1 plus T2 sine of theta 2 minus mg is equal to 0. And now if you look at this equation, here's a T2, here's a T2, and we know everything else, which means that we can solve this equation for T2 and actually get a number. Once we have that number, we can come back over here and solve this equation for T1, and that gives us both of our tensions. Okay? So let's do that. I'm going to start, let me put this up here a little bit. I'm going to start by taking and pulling T2 out of both of these terms and then moving this mg over here to the right-hand side. Now, when I do that, this is not the prettiest thing in the world. When I do that, I get cosine of theta 2 over cosine of theta 1 times sine of theta 1 plus sine of theta 2. Moving the mg over to the right-hand side makes it be positive. Now again, this is not the prettiest thing in the world. I never claimed it would be, but we can already simplify it a little bit because I have a sine over cosine of theta 1. That's a tangent. Okay, so really this is just T2 times tangent of theta 1 cosine of theta 2 plus sine of theta 2 equals to mg. Now things are a little bit easier. If I want to find out what T2 is now, I can just move this stuff over here to the right-hand side by dividing both sides by it. Mg over tan theta 1 cosine theta 2 plus sine of theta 2. All right, so what's mg equal to? Well, our mass was 25.0 kilograms. G is a constant at 9.8 meters per second squared. In the denominator, we have a tangent of theta 1. Now, theta 1 was 20 degrees. Theta 2 is 45. So that's what we have. So let's plug our stuff in. (25 times 9.8 divided by). We have a tangent of 20 degrees times cosine of 45 degrees plus a sine of 45 degrees. Giving me a syntax error again. This is the problem with using a cell phone calculator. So let me use a different calculator. Give me a second. All right, let's see here. Times cosine . 45. So this is a little bit longer. Then add our sine in. I know. All right. Then we're going to take 25, 9.8. All right. So I get, for this one, 254.0 newtons. Okay. Knowing that, we go back over here and plug what we got for T2 into the equation for T1. Now, theta 2 was 45 degrees, and theta 1, remember, was 20. So, cosine of 45 divided by cosine of 20, and then multiplied by okay. So for this one, I get 191.1 or 191.2 actually. Okay. So, so what we have here for our tensions is that T1 is 191.2 newtons. But if you stick to the number of sig figs here, which we have, it's just 1, this would be about 200 newtons. And again, 1 sig fig, this ends up being about 300 newtons. So there would be your answers right there. Now, if you want direction, you can say T1 points with 200 newtons of force, up 20 degrees, basically 20 degrees above the x-axis. And, you can say an equivalent thing for, T2. So, but you get the point. Anyway, long problem, but it serves to show you how these forces, when they're broken up into pieces, can help each other out. Now, so we have another problem here. A Hot Wheels car is released from rest 2 meters up an inclined plane. If the plane makes an angle of 25 degrees with respect to the horizontal, A, what acceleration does the car feel down the plane? B, how long does it take for the car to hit the bottom of the plane? And C, how fast is it traveling? So, let's draw a picture. Actually, let me draw this a little differently just to make our life easy. So here is the X. Here is the plane, like this. And then here's Y. Okay. Now, so from here to about here is where the cart is. The car. Your car has got a mass of, let's see, I don't have a mass on it. That's fine. We don't need it. We're going to find out why that is here in a second. Let's see here. This right here from there to there is 2 meters. So we'll call this delta. That's a good thing to call that. I'm going to call that D for right now. We're going to come back to what that is here in a second. 2 meters. So we're going to release this thing from rest. I'm going to drop the XY notation for the moment. Okay. Its final position in X is 0. Its initial position in X and Y, well, that's complicated. We'd have to find out what it is, right? Using trig. Wow, this looks like a pretty complicated problem. Well, before we worry about the initial position in X and Y, let me show you something. Gravity acts to pull this thing down to the ground like that. This thing is pushing into the plane because of that. So there is a normal force that points up like that. Remember, normal forces always act at right angles to the point of contact here on the plane. Now, what I propose we do is to rotate our coordinate system to make our lives easy. Now, what do I mean? Well, here's our picture right here. Okay? Now, let me see if I can do this. We're going to perform an experiment. So, can I rotate? Yes. If I rotate the problem like this, okay, you see what I've done here? If I rotate this like that, then I could treat this as though it's the X direction. And I can play some simple geometry games to figure out how to break this vector up into pieces. And what I've done is to take a complicated 2D problem. I mean, you really don't want to know how complicated this is. If you try to break it up into X and Y pieces, oh, it just gets nightmarish. And really turn it into a one-dimensional problem. Okay, so the key here is rotating it. Okay, and really remember, you're free to draw your coordinate system however you want. So you could think of it as sort of instead of standing here and looking up at the cart, you've kind of got your neck cranked like this, and you're looking at it like that, like this is the x-axis, which makes sense because it's moving along it. Remember, the plane here is a solid object that prevents it from going beyond its boundary. So that's exactly what I'm going to do, is to rotate it like this. Now, if I rotate it like this, my problem is going to look like the following. And let me get rid of this right here, so we don't need it anymore. So now my problem looks like this. This is the plane that the car is going to move along. okay? And this is straight up and down from the plane, which we're going to call the new y-axis. So here's y, and here's x, okay? Now, if we rotate it like this, and we place our car at the origin of our coordinate system, which we can do, now our initial position in the x direction is 0. The cart starts from rest. Oops, let me re-index that. It's an old way of looking at stuff. Our initial velocity in the x direction is 0. Now, this thing is going to move to the right at this point right here. This is 2 meters away. So look, we have our initial and our final positions. Now, the big question is what do we do about the vectors? Okay, because as drawn, our normal force points up like this. So here's our normal force pointing up from the plane. You can do better than that. There's a normal force pointing up like that, right? So, and here's the plane itself. Remember, it's a solid boundary. But gravity is a bit of a problem. Okay? Gravity, if you take a look, if we make that rotation and you think of this as being sort of up and down, then the question is what is this angle right here? Now, we're going to get to that here in a second, but let me just sort of draw this off kind of like that. Okay? This is going to be the force due to gravity, and the angle that we're dealing with has yet to be determined. Or has it? Because watch. Let's pretend for a moment that I took and put my hand here on this plane and I lifted it like that. Well, as I lift it like this, will you agree with me that this angle right here is going to get bigger? Of course. If you think about the angle between up and down from the plane and gravity, gravity always points down like this, but this always points out at 90 degrees. So as I lift this angle right here is going to get bigger as well. And if I were to lift this thing all the way up to where it was lying just along the y-axis, this would be pointing straight down y, this would be pointing straight down negative x, which means that the angle there would be 90 degrees. And so would this. If I were to close this down now, let's pretend I'm moving it this way. As this angle gets smaller, this angle gets smaller. And when it's all the way down to where this lines up with the x direction, this would be 0, and so would this angle too, because now this would point straight up y, which means that this angle right here and this angle right here are the same. This is theta. That's the same angle. So by making our coordinate rotation right here, what we've done is to really make our lives easy. As it stands here, we would need to play some games to figure out what was going on with the normal force, and it gets pretty nasty. Here, I can tell you that it's this part of gravity, this part right here, that's responsible for moving this thing along the plane. And that's obvious from the picture that we just drew. So, that said, let's draw our force diagram. This is y, and this is x, based off of our new picture right here. There is a normal force that points up. And there is gravity that points off to the side like this. This is theta. Now, this is a dynamics problem, but already we can see, because the plane is an unyielding thing, that the normal force and the y part of gravity are going to balance each other out and give us 0. It's the x part, the part that lies down the plane of gravity, that makes this thing roll down it. So, let's sum up our forces to get our external force, of which we have 2. A normal force and the force due to gravity. Now, these are not going to give you 0, but are going to give you m times a. In the y direction, a is 0 because the forces balance each other out. The normal force is positive. The y part of gravity is negative, and they cancel each other out. In x, though, you only have one force. That is the x part of gravity, and it is positive. And it is responsible for taking and causing the acceleration in the x direction. Now, so that means we're going to have to break up gravity into pieces. Let's go ahead and do that. Here's gravity. There's this. Actually, I'm going to do this a little differently. Since we have the angle down here, we're going to do it this way. Like that. This right here is FGY. This is FGX. And this is theta. And this is FG. Now, in this case, FGX is the opposite side, and FGY is the adjacent side to the angle, which means that FGY is going to equal to FG times cosine of theta this time. And FGX is equal to FG times sine of theta, or mg cosine of theta and mg sine of theta. Okay? Now, so we have our forces. We have our force, our external forces broken up into components. So let's plug things in. We'll start with the top one, which says that the normal force and the y part of gravity cancel each other out. Then we have this equation right here, which says that the x part of gravity is what's responsible for the acceleration. And look, the masses cancel. So the acceleration in the x direction due to the plane is just g times sine of theta. Okay? What acceleration does the car feel down the plane? Well, I'm glad you asked. 9.8 meters per second squared times sine of 25 degrees. .14 meters per second squared. Okay? Now we'll round that in a moment. How long does it take for the car to hit the bottom of the plane? Well, let's write down our kinematic equations. Just 3 and x, as opposed to, if we had worked it this way, 3 and x and 3 and y. So, Vx is equal to V naught x plus Ax times t. X is equal to x naught plus 1/2 Ax times t squared plus V naught x times t. Vx squared minus V naught x squared is equal to 2Ax x minus x naught. Now take a look at what we've been given here. Did we even write out our givens? Huh. Well, I guess I got too excited, huh? About the whole coordinate system rotation thing. Well, goodness. Well, let's write our givens then real quick, based off of this picture. Because this picture tells us our initial velocity in x is 0. Our position is 0. Our final position is 2 meters, right? Our angle is 25 degrees. We're trying to find Ax, T, and V, x. right? So let's plug in our stuff now. Initial velocity is 0. Initial velocity is 0. Initial velocity is 0. Initial position, 0. Initial position, 0. So again, Vx is equal to Ax times t. X is equal to 1 half Ax times t squared. And Vx squared is equal to 2 times A sub x times x. And we have options here. We've already found the acceleration. How long does it take for the car to hit the bottom of the plane? I would use this equation to do that. We know x. We know it's 2 meters. We know everything here except for t. And if you do that, t is equal to the square root of 2 times x over a sub x, which is the square root of 2 times 2 meters divided by about 4.14 meters per second squared. Remember, you want to use the full expression of that. So you store it in your calculator, your crapulator. So let's see, square root of 2 times 2 divided by that. I get 0.983 seconds about. Now, the last thing we want to find is how fast it's going. I would probably use this equation to do that, since we have everything that we need. We don't have to plug in something that we've explicitly calculated, with the exception of the acceleration. So here, Vx would equal to the square root of 2 times a sub x times x, or the square root of 2 times 4.14 meters per second squared times 2 meters. So, again, use a full expression. I get 4.07 meters per second. Now take the positive value because it's moving to the right. So, what acceleration does the car feel down the plane? 1 sig fig here, 2 sig figs there, which means that we would round this to 1 sig fig, 4 meters per second squared. How long does it take for it to go down the track? This rounds to 1 second. How fast is it going? This rounds to 4 meters per second. Which, if you think about it, makes sense. Your acceleration is 4 meters per second. You're traveling for a second. How fast are you going? 4 meters per second. Okay? So, there's that problem.